Picking back up with lesson 6.1, we left off on the previous video. You can see that really what we did not do was finish up this integral. You can finish it up via the calculator and arrive at an answer very quickly. In fact, for the homework that we're going to be doing for tonight, we're primarily concerned with setting up the integrals. We're going to let you evaluate them with the calculator. Obviously, we want to be prepared to go by hand too, but to get us started, we'll let the technology help. As we move to the second page, however, you're going to see that x could equal f of y. We've seen this in the past where instead of y equals some equation, maybe we'd have x equals some function of y. The roles of x and y are switched. You can see in this picture, we could most certainly have an enclosed region. And what you would do is integrate with respect to y. You'd build rectangles off of the y-axis, going from a C to a D here. And what you will always do as you're integrating with respect to y is work right minus left. Just as we had top minus bottom, we're going to have right minus left. And you will be able to always evaluate the area enclosed that way. So here you can see we've got a very similar setup. So without a doubt, this is something that kids can feel considerably more uncomfortable with. Take a look at x equals y squared minus 3. We can graph this with technology if we solved for y, for y1 and y2. It's more important to be able to do this without a calculator, though. So much of the AP exam has no calculator allowed, so we have to be prepared to reason things out. To get to the heart of the matter, when you first graph, you make a table. And when you were graphing many years ago, you'd start by plugging in x values. We could plug in y values. If I let y equal 0, 0 squared minus 3, we'd have x equals negative 3. Let y equal 1. 1 squared is 1. 1 minus 3, you'd get negative 2. Let y equal negative 1. In a similar way, you'd get negative 2. We could proceed with this. We could definitely let y equal 2 and so forth. But I hope you remember from your days in pre-calculus in AMA that you were graphing parabolas just like this, x equals y squared minus 3. And what you could very quickly remember is when you have y squared, you'll either have a parabola opening to the right or towards the left. Because y is positive or y squared is positive, you would have good reason to believe that you're opening towards the right. And you are. You'd get that confirmation very quickly by just plotting a few points. And it wouldn't take long for you to quickly see that this is a parabola that opens towards the right. In a very similar way, you could do the same thing right here, making a table. It wouldn't take you too long to let y equal 0 and see that x would equal 0. And, then if you'd let y equal 1, well, my goodness, you'd be at negative 2. So, surprisingly, you'd say, I just hit that point. And if you let y equal negative 1 in a similar way, you'd get that way too. So here you are, you're dealing with this parabola opening towards the towards the left, so sorry. And, without even using a calculator, you could very quickly come up with what is happening here. So, what you have are boundaries going between negative 1 and positive 1. And you could see if we built a rectangle going in this y direction, stacking in a vertical direction, your right boundary would always be the same as would your left boundary. So we're going to do what the top of the screen is telling us to do. We're going to integrate from negative 1 to 1 with a dy. We're going to do right minus left. And the right boundary is this negative 2y squared. The left boundary was the first curve that we graphed. That's the y squared minus 3. Now again, this is not a hard integral to work out. You could most definitely get this thing to simplify quickly, and using the fundamental theorem would not be difficult at all. You could even use some even functions to speed through this. That being said, you could just as well, get some help graphing this thing out with the calculator. And, I mentioned at the beginning of the video, of this video, that we finished up the previous problem in that regard. You could, in fact, type in a negative 3y squared. Just want to make mention that, x is so common, we could just treat x as if it really were a y. If you wanted to do an alpha y, you could do that. You would actually get the same answer. End of the story, though, is that the bounded area is that of 4. Let's take a look at this next problem. We're going to have area bounded by y equals radical x, y equals negative x equals 1, and x equals 4. We could find the area either by integrating with respect to x or with respect to y. We'll just do one or the other. We won't do both. You always could make a problem work out in either direction. It just might be way more difficult to do so. Look, y equals radical x. It's actually half of a parabola opening towards the right. It would look something like so. Y equals negative x, of course, is a line. It would look just like so. And x equals 1, well, you could see that's going to be a vertical line right here. X equals 4, that would be a vertical line also. And you can hopefully see very fast that you have enclosed a region. You can find the area of what I am highlighting in yellow. Now, one of the biggest, most important questions that we can address is, should we integrate with respect to x or with respect to y? I do want to make a quick observation that if you wanted to do the problem the way we had before, the last problem, you'd actually have a lot of difficulty. You'd have a right minus left boundary here. The left boundary is the line y equals negative x. But look up here. If you move up just a little bit, your left boundary is no longer the line y equals negative x. Now it's the line x equals 1. Likewise, up on top, you would have a left boundary of being this square root function. What are we getting at? Plain and simply, integrating in that direction would make the problem way, way tougher. You'd have to do 3 distinct integrals to make it work out. And plus, you'd have to solve for x equals for every one of those equations, and that could be a little bit of a struggle there. But look what happens if instead we just make a rectangle in the x direction, the rectangles that we're so accustomed to drawing in. What I'm getting at is the top boundary would always be radical x, that y equals radical x. Down below, the bottom of the rectangle would always be negative x. That's the way to approach this problem. We're going to do top minus bottom, and it becomes way, way, way simpler. The top is radical x. The bottom is this negative x. And rest assured, we could work this out quickly by hand. But again, for not only the sake of this video going more quickly, but also, just to give you more practice getting the setups of your integrals correct, we're going to allow you to use your calculator on all these problems tonight. So it would only take a moment to get this all typed in. And as we hit enter, You can see we'd get 12.16 repeating, it looks like. If we turn that into a fraction, we'd get 73 over 6. And that's how you could find your bounded area. Let's move on to this next problem where we need a calculator. As we graph this thing, and you can see that we actually graphed this in class, we typed in y1 was the first function, y2 was the second function. If you were to very quickly get the appropriate window, I think you'd see that Zoom 4 does the best trick here. Zoom 10 doesn't quite do the same justice, but the first curve is that curve that looks something like a parabola, not quite, obviously. It's a polynomial, and you can see it looked like this and then came down. The other curve looked something like this. Both curves are going to have the origin included. At this point, you can see that we do have some enclosed area. If you were to let x equals 0, you'd see that you'd get 0 for both of your curves. The bigger question is, what is this other intersection point? You could very quickly see top minus bottom is held to be in a constant, always top curve minus bottom curve here. What I'm going to do is hit second, calculate, and go to the intersect tool. And it will say first curve. By the way, up on top, you can see it's that polynomial. Hit enter. Second curve, it's that other radical function. Hit enter. And then guess. Put your cursor about where it looks like they're crossing. You'd get about 1.180, something like that. I'm going to hit second quit. And then I'm going to hit X. And sure enough, that last X value is still there. I'm going to hit store. It's right next to the 1. I'm going to hit alpha A. And what I've just done is I'm having alpha A be that 1.18, whatever it is. I want the calculator to remember that for me. Now, I'm going to integrate from 0 to A. My first curve, the top curve that we're going to have to deal with, the top curve was this radical function. So we'll have that thing typed out there. That's your top. Your bottom is that polynomial, x to the fourth minus x. So I'm going to get this thing typed out real fast. And I'll hit math, and we'll come down here to fn int, and we'll say 0. Bring this up and do an alpha A. Now, I could retype all of this, but y2, the second function that I typed in, is what I really want to hit. I'll press vars, yvars, hit function, and bring down y2. That's my top. The bottom is vars, yvars, function, y1. And now I can work out very quickly that the area is roughly 0.785. Okay, one last thing to take a look at. The area between curves, especially if they cross each other multiple times. Look at F and G, and you can say, wow, we've got this bounded area. How in the world can we deal with this if we've got multiple intersections? If you have a calculator, the answer would be just integrate the absolute value of F minus G, and that would work out very nicely. Otherwise, you'd have to find this intersection point and deal with the top minus bottom boundaries changing. Good luck. Hope it's going well.